Okay, in this question we have a rectangular coil of 3 centimeter and 5 centimeter sides, something like this. It is oriented so that its plane is perpendicular to an external field of 0.8 teslas pointing up. If we take up out of the page, this is the look of B equal 0.8 teslas. The magnetic field changes during the course of 0.5 seconds to 0.20 teslas pointing down. So the new field is going to be pointing down, so this way, 0.2 teslas, and it's going to take 0.5 seconds to go from this field to this field. The question is asking us about the average induced EMF in the coil to the nearest 10,000th of a volt. Okay, so the EMF is given by minus n delta phi delta t. In this case we have only one coil, so it's going to be minus delta phi over delta t. Now delta phi is going to be phi final minus phi initial. So and in this case phi final is going to be B final times the area, and phi initial is going to be B initial times A. If we take the upward direction as positive, phi final is going to be minus 0.2 teslas times the area, which is the 3 centimeters times 5 centimeters, so that's going to be 3 10 to the minus 2 meters times 5 times 10 to the minus 2 meters. This comes out to minus 3 10 to the minus 4 Webers. Phi initial is going to be plus in this case, since the field is pointing up, 0.8 teslas times the same area as we have here. So we should end up with (12 10 to the minus 4 Webers. Now the EMF is the change in flux, so it is going to be minus 3 minus 12. Of course these are in Webers over the time, which is 0.5 seconds. So minus 15 over 0.5, so that should give us 30, and then we have the 10 to the minus 4. So it's 30 10 to the minus 4 volts. So that's our answer. Okay, the next question, we have a coil of diameter 10 centimeters. It consists of 20 turns of circular copper wire of 2 millimeters in diameter. Let's change the color of this to red. The magnetic field perpendicular to the plane of the coil changes at a rate of 3.56 10 to the minus 3 teslas per second, and the resistivity of the copper is given by this, and we are asked to find the current in the coil. Okay, now the current in the coil is going to be given by the EMF over the resistance. In this case, they didn't give us the resistance, but they gave us the resistivity of the coil, of the wire that makes up the coil, and they give us the dimensions of that wire by giving us the diameter, how many turns, and its diameter as well. R, if you recall, is resistivity, length over A. In this case, the resistivity is what we have here, 1.68 10 to the minus 8 ohms per meter. That's my rho. My L is the length of the wire. The length of the wire is going to be how many turns times the circumference of each of the coils. So the circumference is pi times the diameter. So in this case, that comes out to 20 times pi times 0.1 meters. So that gives us about 6.28 meters. So this is my length. And then for the area, this is, remember, the area, the cross-sectional area of the wire. We have the diameter, the area is pi r squared. So it's going to be pi times 1.3 10 to the minus 3 meter squared. And in this case, that comes out to be about 5.3 10 to the minus 6 meter squared. That gives us a resistance of 0.0920 amps. Ohms. Okay. Now we found our R. So the missing part, the EMF. Now how do we find the EMF? The EMF is minus N delta phi over delta T. But what's delta phi? Delta phi is delta of B times A over delta T. Phi, the flux, being the magnetic field times the area. We don't have an angle here, a cosine, because it's perpendicular. So it's cosine of 90 degrees. So in this case, since A does not change, this ends up being minus N times A. Remember, this A is different than this A. This A is the area of the loop of the coil. So NA times delta B over delta T. Delta B over delta T, that's given. Okay, now N is given. A, we can calculate it. A, in this case, is pi r squared. Let's not confuse that with the resistance, radius squared. Now the radius here is going to be half of the diameter, so it's going to be pi times 0.05 meter squared. So we plug in everything. Do it here. So that gives us an EMF of 5.6 10 to the minus 4 volts. Then that gives us a current of E over R of 28 milliamps. Now in this question here, we are asked how fast must the flux change in Webers per second in a 0.25 meters squared. So we have the area here. We have n 10-turn loop placed in a magnetic field whose maximum value is 1.5 teslas in order to produce an EMF of 24 volts across the loop. Okay, so EMF, it is given by minus n delta phi delta t. So what are they asking for here? Webers per second. That's really what they are asking for, delta phi over delta t. So most of what's given here is not needed. All what we need is delta phi over delta t. That's going to be equal over n. So now here the minus sign is just tells us nothing really. We need the absolute value. So in this case, that's going to be 24 volts, I'm sorry. Over the number of turns, which is 10. So it is going to be 2.4 Webers per second. In this question, we are told that an electrical generator was designed to produce an RMS voltage of 110 volts AC by rotating at 20 turns, so that's n loop, at 3600 rotations per minute at a constant magnetic field of 0.7 teslas. And it is asking us about the area of the loop to the nearest centimeter squared. Now, let's remember that the EMF, the maximum EMF due to a generator, is given by N, A, B, omega. N is the number of loops that's given. A, that's what we are looking for. B is given, 0.7 teslas. Omega is the angular speed in radians per second. They are giving it to us here in rotations per minute. So that's the first thing we need to do. Omega, 3600 rotations per minute. So that's going to be 3600 times 2 pi radians per rotations over 60 seconds per minute. That should give us our omega, which is 377 radians per second. Now, the other thing we need to pay attention to, this is the maximum EMF, but here they give us the RMS voltage. So to find the maximum voltage or the maximum EMF, it's just square root of 2 times VRMS. So in this case, that's going to be 120 volts times square root of 2. That comes out to be about 170 volts. So my A is the EMF, the 170 volts, over N, which is 20, times B, which is 0.7, times omega. And that comes out to be 0.032 meters squared, but in centimeters squared, that's 321 centimeter squared.